All right. Sorry. So we have quite a bit to do today. And so two things. Number one, we have some problem sets from chapter 4, which we just completed before the long gap in our classes. I don't remember. What were they about?
So I had sent you my answers for the midterm along with a reminder that I did. So I'm not sure if you saw it or not.
Want to know what?
I sent you the reminder that I had done my midterm, and I sent you the answers along with it. But some of the images, I don't know if they sent correctly.
Oh yeah, no, I haven't started looking at them yet. I'll let you know if there's a problem.
Okay, thank you.
Yeah, it does occasionally happen with PDFs or photos, but it's almost always possible to read them, but very occasionally it's just not going to happen. So if that happens to you, I'll just let you know.
All right. And if anything, we could just have a one-on-one Zoom meeting with me talking about what I did, right?
Right, after they're all corrected, yes.
All right, sounds good.
Okay. All right, anyway, so yeah, chapter 4, we just finished it. Our discussion about logarithmic and exponential functions, as a matter of fact. And there were two problem sets that go along with that chapter, which we'll do right now. And then 5, we kind of started it, but it was 2 weeks ago. So I think we'll have to start that one more or less all over again. And that should take care of today. Next week, I think we're switching over to chapter 9, which is a discussion about linear equalities and inequalities. And so, of course, we're getting towards the end of the course. So we are running out of time a little bit here, but that's all right. We'll finish everything in plenty of time. The finals week is not until, I think, the week of May 13th. So we do have some time left. In fact, why don't we look at the calendar? Today's the 21st, right? So so today's the 21st, next week is the 28th, and then the 6th. All right. So what does that leave? 28. Today, the 28th, and the 6th. Okay, so that's 3. And then the week of the this next week in May, the week of the 11th, I think the finals. Oh, wait a minute. No. This calendar starts on Sun. Oh my God. All right, let's try another one. That calendar was starting on Monday, so it was all completely. Here we go. So let's try that again. Today's the 21st. Next week's the 28th. Then we have the 5th and then the 12th. The official starting date of the final exams is the 13th. So altogether, including today, we have 4 sessions. All right. So let's keep that in mind as we go along. And so that should be plenty of time to finish the material and review. So why don't we get into it? So what I'm going to do is open up the chapter 4 problem sets. And let's see what we were doing. All right, so chapter 4, there were actually 2 problem sets. Number 1, of course, and number 2. All right, so hold on one second while I save these. And then number 2 is right here. All right, good. And also, I actually did manage to find a couple of videos which explain what we're doing with the trigonometry. And they're actually kind of interesting. One of them is about how to do the calculations. One of them is more about how they're used in practice, which is kind of interesting because you might say to yourself, well, when will I ever see this stuff again? But the reality is you will see it, or at least even if you're not working in that area, you'll definitely encounter trigonometry in a lot of different surprising areas. But no, we'll save that for later. And so right now, we'll just focus on these problem sets. So let's start. Oh, not that one, this one. Okay, so hold on one second. All right, so these are our exponential functions. And if you recall from all that time ago, an exponential function equals or takes this form. And it can, depending on the size, sign of A, it'll often look either like this or possibly like this. So what we're trying to do here is identify what exponential function is represented by these points. Okay, so in other words, just like with a straight line, you can identify uniquely the equation for an exponential function if you have just 2 points. That's all you need. Although it's a little bit more involved than with a straight line, of course, because with a straight line, you're basically solving for 2 pieces of information that are linearly related to each other. These are not linearly related, although they certainly are related. Now, let's keep in mind that in each of these cases, this is what we mean by f of x. Sorry, this is x, this is f of x. So we're going to go through one at a time and plug in those numbers into this general formula. So for example, in the first case with 1 comma 6, what we're seeing here is that 6 equals AB to the first power. Or you can simply write it as 6 equals AB. For the second case, we have 750 equals AB to the third power. So clearly we have 2 equations and 2 unknowns. Now, these are not linearly related to each other, so we can't really use the method of simultaneous equations, but we can use the method of substitution. So what we can do, for example, is come over here and solve for A. And then that A can be substituted over here. So we'll have 750 equals 6 over B times B cubed. And so we're going to then have 750 equals 6B squared, because here, this is a 1. B cubed, I'll put a little note over here, B cubed over B1, of course, reduces to B squared. And so this is our expression for B. Now here, we can solve for it directly because there's only one unknown. So I'll divide out the 6 from both sides. All right. So 750 over 6 is, let's see, 125. Okay, so 125 equals B squared. So obviously then B is the square root of 125, which we can simplify a little bit. You can rewrite this as radical 25 times 5. And then that would give us the product of 2 radicals. And then finally you have 5 radical 5 equals B. All right, now what do we do with that information? Let's come back over here where we know that 6 equals 6 over B equals A. So now we know that 6 over 5 radical 5 equals A. Now, in a case like this, hold on a second, wait a minute. Okay, just hold on one second. So yes, so how do we simplify this? Normally what we do here is we don't like to have radicals in the denominator just by as a matter of convention. So what can we do about it? We can multiply this expression by radical 5 over radical 5, and that certainly will not change our results. And so we have 6 radical 5. Now here, 5 radical 5 times radical 5 is 5 times 5. So we'll end up with 6 radical 5 over 25 equals A. And let's see. How can we simplify that further? Well, okay, we can divide. I'm not sure if we can simplify that any further. Well, that's okay then. If that's our answer, that's our answer. But then the bottom line is, remember, we're aiming for this equation up here. So f of x is, of course, ab to the x. And so now, even though it's not a very attractive looking formula, it certainly is in the right form. This is A. B is 5 radical 5, and that's raised to the x power. Okay. So we've got 6 radical 5 over 25 times 5 radical 5 to the x power. And that's our expression, or that's our function. Okay, so the purpose of all this was to show that these 2 points are on this line. In other words, are on this curve. If we plug them back in, although there's no real need to do that, you could prove, unless you feel like double checking, that each of these does actually work. For example, 1 comma 6. Why don't we try that one and just see what happens? So what I'm going to do is put in 6 equals, and I'm hoping that this works. If not, then something's terribly wrong. Okay, so x is the exponent. This is f of x. So let's see if this is actually true. When you multiply the numerator, you'll get 30 times 5. In the denominator, you still have 25. So in other words, 6 radical 5 times 5 radical 5. You're multiplying these together. And then, of course, you're multiplying the radicals. So you'll get 6 times 5 times 5, okay, which is 30 times 5, or 150. And that does, in fact, equal 6. All right, so that one works. The other one, we don't have to do this every time, by the way. 750 and 3. We might as well double check them both. Then going forward, we don't necessarily need to do this every time. Okay, so the original function was here. I'll just copy it down below. And then we'll substitute what we have. And let's see if we got it right. Well, we already know, I mean, I guess it's not likely that the second one will be different, but let's do it anyway. So that means that 750 should equal this. All right, let's find out if it does. Now here, this expression what you can actually do is treat it like 5 cubed times radical 5 cubed. And so we can write it like that. And then let's see what happens when we multiply them together. Five cubed is actually 125. And then we'll keep this the way it is. Now, when I multiply these together, let's rearrange this slightly. And so when you multiply radical 5 times radical 5 cubed, what you end up with is radical 5 to the 4th. And so radical 5 to the 4th is the same thing as 5 squared, which is 25. Okay, so we actually have here 750 equals 6 times 125 times 25 over 25. 750 equals, now these cancel out, 750, and we're done. So that means obviously it worked. Okay, whatever we did was correct. So this is our final answer. And we just proved that it is in fact correct. Okay, it's a bit of a mess, but it works. All right, and you can't always expect beautiful equations. Sometimes you end up with a mess like this, but this is what the function looks like. Okay. All right, I have to do one more thing here. All right, let's go to the next one. Now they're all exactly the same. So we need the practice, of course. So f of x was ab to the x. And so we substitute the 2 points. So remember, this is x, this is f of x, this is x, this is f of x. So we'll start with 1 comma 2000. That means that 2000 equals ab to the first power, or 2000 equals ab. And for the second equation, we have ab squared, and we're done. Now, as we did before, what we'll probably want to do is take one of these two and rearrange it algebraically so that we can replace it in the other expression and come up with an equation in terms of just one variable. So let's do the first one. It looks easy. 2000 equals AB, which means that 2000 over B equals A. Fine. Now we can combine that with the second equation. The A will be replaced by 2000 over B times B squared. And so you've got 20 equals, now B squared divided by B is just B. So I'll divide both sides by 2000. And this works out to be 0.01. Or 1/100th. You can leave it as 1/100th if you want. It's probably easier to write it as 0.01. Now, once that's in place, it's a very easy matter to substitute this back into either equation. But let's go back to the first one. We know that, wait, hold on. 2000 equals AB. I just replaced B with 0.01. Now I'm going to divide both sides by 0.01. And that tells me that A equals 200,000. Wow. So the original format of this equation is f of x equals ab to the x. So that means that this function looks like this. And b is 0.01. And that's it. We're done. So I don't think we necessarily need to double check every single one of them, but I mean, it was important to see at least once how this would be done, just to make sure you haven't messed up anything. All right, now here's another one. And again, the function we're looking for is this. And this is x, f of x, x, f of x. So we'll do these both. Let's start with -2, 6. And that tells me that 6 equals ab to the -2 power. In the second case, this tells me that 1 equals ab cubed. Now, these will be a little bit more challenging to simplify, I would say. Why don't we do this? This is the same thing as saying a over b squared. Okay, just a quick reminder. So therefore, if I cross multiply, oh, that turned out not to be so painful. I've solved for a. I can plug it into the second equation, 1 equals ab cubed. And now I can replace the a with 6b squared. And so this tells me that 1 equals 6b to the 5th power. Whoops. Now, how does that help? Well, actually, I shouldn't have circled that. We're not done yet. If that's the case, then what do we do about b? That tells me that 1/6 equals b to the 5th. And then, wow, this is really a mess, isn't it? How do you solve for b? You raise both sides to the 1/5 power. These cancel each other out, and you're left with 1/6 to the 1/5 power is b. And then we need to find our a. So up here we were told that a equals 6b squared. And now we're told that b itself is 1/6 raised to the 1/5 power. All of that is squared. Wow, what a mess. So this equals 6 times 1/6 to the 2/5 power. And why is that the case? Just as an aside, anytime you have something like this, let's say you have a to the b power times c, this is a to the b times c power. So those are two very, very scary looking formulas or expressions, but they are correct. So when we bring them together, our final result will be 6 times 1/6 to the 2/5 power And then, oh my God, look at this. We have 1/6 to the 1 over 5 power, all raised to the x power. Now that's a messy formula. Or expression. That's a mess. But that's what we have. So when we have exponential functions, we often end up with these incredibly messy expressions, but that's because of the way they are structured. So wow, that was bad. Now, if you needed to, if you really want to simplify it, you could take this, for example, say, I really want to know what these are equal to. Just in case, let's try that. Go to your calculator. So the first one is approximately equal to 2.93. The second one is approximately equal to 0.70. So if you'd rather replace all of this with the following expression, that's perfectly fine. That works too. In fact, I think it's a lot less scary than what we have up here. That's up to you. In fact, we could have done that up here too, I guess. No, this one was fine. There's nothing wrong with this one. It works beautifully. But this one was so catastrophically messy that I think you might want to do something like this to take its place because, ooh, this is a mess. All right. All right. Now, what about this one? All right. So once again, we have f of x equals ab to the x. And so we'll start with the first substitution. Let me just save that for a minute. Okay, here we go. So in the first case, we have 1 equals ab cubed. And in the second case, we have 4 equals ab to the 5th. So again, these will not be easy to carry out, but we can do it. So like for this first one, if we want to substitute for a or solve for a, we just divide both sides by b cubed. And now we'll plug that in over here on the right-hand side. And of course, this is the equivalent of saying that 4 equals b to the 5th over b cubed. And now you can apply the so-called quotient rule, which basically says that this equals b to the 5 minus 3 power, which is b squared. So that's a little reminder. So that means that this 4 equals b to the 5th over b cubed is nothing but 4 equals b squared. Then that worked out well because now obviously 2 equals b. And therefore, if we come over here, 1 over 2 cubed equals a, 1/8 equals a. So that one actually worked out rather nicely. Surprisingly so. Yeah, I'm still kind of startled to see how simple it was. All right. So the final result would be, therefore, f of x equals 1/8 2 to the x power. Okay, those are done. So that took forever, but that was worth it because that takes a lot of practice, I think. So now, say that again, we're looking at interest rates again. So the formulas that we used here, let me just remind you, the most important formula in this section was this one. Let me throw it in here with the equation editor. And you'll recognize it as the future value of a sum formula when there's compound interest. Then we have 1 plus 1 over, R over n to the nt power. Where, let me remind you that A is the future value of a sum. P is the principal, and the amount borrowed or lent. R is the rate of interest, which is, you should express it as a decimal. N is the compounding frequency, which means number of times per year that interest is compounded. And then T is time, measured in years. So all of that information will provide you with the future value of the sum. Given the information that you have, you can figure out how much you'll have in the future based on what you have today. All right, so for example, let's look at this one. An investor deposits $10,250 into a bank for 10 years. So the amount invested is the P, or principal. It's a 10-year deposit. The rate is 4%, but the compounding period is quarterly, or frequency is quarterly. What's the future value of the sum? Okay, so let's plug in some numbers. All right, so first we simplify, of course. So we've got 10,250, and then we should have 1 plus R is 4. It's a quarterly compounding, and it's a 10-year investment. So probably your best bet is to reduce this to the simpler version of 1.01 to the 40th power. That, in my opinion, is the way to go. And then you take out the calculator. And let's see what we get. All right, so I'll take out my calculator and get, let's see. I've got 15,000, 260.85. Now, you may have something slightly different due to rounding considerations, but that more or less should be your answer. Okay, now, and by the way, when you're doing this on your calculator, what I think you should do is, rather than try to go from left to right, it might be simpler if you calculate 1.01 to the 40th power first, and then multiply that by 10,250. You can certainly go from left to right, but if you do, you'll have to use the parentheses very carefully. If you start from the right, you could actually, let me just show you how this could work. Let's get this out of the way. 1.01 to the 40th power. The only thing is you have to be a little careful not to get any too many rounding issues. 1.01 to the 40th is approximately equal to 1.488863734. And when you multiply that by 1.488863734 times 10,250, you should get within a penny of the correct answer. Yeah, because remember, you're rounding this to dollars and cents because it's money. So therefore, and that's just me. I mean, you can do it. If you go the other way, you would have to do something like this: 10,250 times, and of course that X means times on your calculator. Then you need to open the parentheses, 1.01, and then you need to use the exponentiation key. And depending on which one you have, it could look something like this: X to the Y, for example. And then you need 40. Then you have to close and you'd have to hit the equal button. So in other words, you can see the potential exists to go wrong in this if you're not careful with the sequence of parentheses and equals. But this will work. I don't know about you, but I think it's a little bit easier to do this. Oops. Okay. Oh, what happened? Okay, so I don't know. It's just me. I think this way is a little quicker and easier, but you can use this approach as well. That's up to you. And if you have a high-end scientific calculator, that helps things a little bit too. But you still, no matter what you do, you have to be careful. Now, in question 6, they're asking us to change the compounding frequency, just the compounding frequency. So n becomes 12. The rest of these numbers are the same. All right, so let's do that. And before you even get started, it should be clear that whatever number you get, it'll be larger than it is now. Because the more frequently you compound the interest, the more interest you'll earn, and therefore the future value will be that much higher. So I'm going to take this, I'll borrow this equation and plug it in, and then the only thing you'll see different is that the two ends switch from 4 to 12. 12. Now, the only thing too, if you're going to round this, so now what's going to happen is instead of having 1.01 here, the exponent becomes 120. 4 divided by 12 is unfortunately a repeating decimal. So in other words, it's 00 and then a bunch of 3s. So the question is, when do you stop? Well, I don't know. I think 1, 2, 3, 4, 5. That's probably good enough. Because remember, we only need to be accurate within dollars and cents. All right, and then you'll, of course, now this time, the correct answer is, let's see. Remember, too, don't forget the exponent is now 120. And so that gives us 15,281.03. So as we predicted, remember before it was 15,260.85. So it did go up by over $20 just because the frequency was changed. All right, so this is sort of a hint. You're supposed to pick up on this. The more frequently interest is compounded, the greater will be the interest earned, and therefore the future value will be greater. Okay, so that's just a note. It doesn't ask you that, but I just want you to see that. All right. Now, in part 7, they want you to go back to the original assumption of quarterly compounding, but they want you to change the time from 10 to 20 years. So let's do that. Let's go back and grab the original numbers. And this time, instead of changing the frequency, we'll change the time. Okay, so time is now 20. All right, so I'll just borrow this equation again. All right, so now we're back to quarterly compounding, but t right here is now 20. All right, so I only have to make one change. The exponent is now 80 instead of 40, but the interest rates are the same. The compounding frequency is the same. So if you take out your calculator, let's see what happens. Uh, 22,721.33. So I'll just make a note here with 10 years, A equals, so just as a quick reminder, so you can see them side by side. This is what we got before with 10 years. All right. And so you can see the difference is quite considerable. So the lesson we're learning here is that as the time over which the time frame over which an investment is made increases, the future value. Well, I guess what I should have said is the interest earned increases, and so therefore does the future value. Okay, so you get more interest and the future value has to go up because you've left the money there longer. Now that's just common sense, of course, but here we're able to prove the exact increase in the future value by using this formula. So this is something to think about when you're investing your own money. So in other words, the longer you leave it there, the more money you'll have. And so this is a good way to think about retirement planning. Okay, now I know it's a little early for you to think about retirement planning, but if you started investing now, by the time you get there, it'll be worth an awful lot of money. So anyway, what's next is, oh, there's one more. Here we go. So here what's happening. Oh, this is just another future value problem, but the setup is a little bit different. So let's grab our standard formula. This one. So it says how much will our deposit is 6,500. That's our principal. The rate is 3.6%. We'll call that 0.036. The compounding frequency is semi-annually, which is twice a year, and the time frame is 20 years. And once again, we're being asked to solve for A. All right, so this is a completely different problem, but it's still a future value problem. So we have, let's plug in some numbers. P is 6,500. Then we'll have 1 plus, and that ratio is 0.036 over 2. And the exponent is 2 times 20. And so if we simplify this, we'll have 1.018 raised to the 40th power All right, and so what does that work out to? That equals 1.018 raised to the 40th multiplied by 6,500 is 13,268.58. And that's it. We're done. All right, now for these next 4 problems, what's happening here is that what we're being asked to do is simply substitute a specific value for x. Okay, so let's see how that works out. So we have, now see, it says f of -3. That means you're supposed to replace all the x's with -3s. Now, technically, I mean, you are done, but why don't we see if we can reduce it to something a little simpler? Okay, so I think you'll agree that 2/5 to the -3rd power is kind of awkward. 2 over 125 is the actual answer. And if you want to turn that into a decimal, that turns out to be 0.016. Okay, so yeah, I think we'll go with that, 0.016. If you need this information for something specific, it's the input to another problem, let's say. 0.016 is a lot simpler to deal with, I think, than 2 times 5 to the -3rd. All right, now this one's a little bit more complicated. If you look at that exponent there, so the exponent is going to be altogether, oh, look at that. How easy. Yeah, no, that's it. Well, that was shockingly simple. All right. How about this one? Oh, well, this one, yeah, you know, in a case like this, with E, anytime there's a power of E, we'll just leave it like that. If you want to know the exact value, it's approximately equal to 20.08 55, let's say. And that's fine. But you can, normally notation wise, you can simply leave it as e to the 3rd if you want to. It's simple enough. Let's put it that way. All right. Now this last one, oh, here's more E. Another one involving E. So we'll plug in -1 for X. And basically, once again, you could just leave it like that. But if you go to your calculator, you'll discover that this is approximately equal to -0.27. Okay. All right, now this next one is clearly an exponential growth problem. We have foxes. All right, we have foxes running around, and so we know a few things. Now, you might recall from the notes that with this specific situation, when time is involved, we typically rewrite our exponential expression according to something like this. Okay, in other words, it's the same thing, but because it's time, often we like to replace x with t. It doesn't really matter, but it makes more intuitive sense, I think, when you're thinking about time. But the one thing you've got to be extra careful about is this. T is time. You will not use these actual years. Instead, if you're being told that the foxes have a certain population in 2012, that means that 2012 represents time 0, the starting point, which means that 2020 represents time 8 years later. If you use the years, you'll definitely get the wrong answer because the formulas were designed with this in mind, with t equals 0 as the starting point, and t equals 8 would mean 8 years later. Now, also don't forget, we originally said that A represents the initial value in one of these cases, and B is 1 plus the growth rate. All right, so with all that being said, we can go ahead and plug in some numbers. We're trying to figure out how many foxes there will be in 2020. Therefore, T is 8. The initial value, A, actually, before we do that, let's identify A and B. A would be 23,900, and B, the growth rate is 9%. That implies that B is 1.09. Okay, that's another important detail. Remember, it's 1 plus the growth rate. It's not just the growth rate. So that's really the only tricky part here. If you got those wrong, well, clearly you're not going to get the right answer. So the two tricky parts were getting the years set up correctly and identifying the values of A and B. Once that's done, it's a breeze. Okay, watch. N of 8 is 23,900 times 1.09 to the 8th. And so what you might want to do is figure out 1.09 to the 8th power first. It's almost exactly 2. It's 1.9926, let's say. Now, in a case like this, keep in mind that the number of foxes has to be an integer. So we may have to do some rounding. When you multiply this out, we have 47,622.25. And so we're going to round this to 47,622. All right, because again, we can't have a fractional fox, so we're going to round that to 47,622. Very good. Now, this next one is a similar idea, except that we're solving for something different. All right, let me just leave that there for a minute so you can catch up. But the next problem involves a house. And instead of asking you for the future value, what you're being asked for is the growth rate. Okay, so algebraically, we have to be a little careful here. Okay, so first, what do we know? So you can see time is involved. So why don't we use this formula? The house in 1985, that will be T0, had a value of 110,000. That's our starting point. 20 years later, the value was up to 145. Now that is actually N of 20. All right, that was the challenging part, because before we were given A and B and we were asked to solve for the future value. This is the future value. All right, what we're looking for here is the growth rate. Okay, so what do we do now? All right, well, first of all, let's write it out as N of 20 equals AB to the 20th power. And then let's make some substitutions. 145, A is equal to 110,000. B was which is what we're looking for, is raised to the 20th power. So the next step is to divide out, of course, both sides by that 110,000. Okay, and that ratio is approximately equal to 1.31818. That's probably good enough. Now, in order to get rid of that exponent of 20 there's a couple of things we could do, but why don't we do the simplest one? I'll raise both sides to the 1 over 20 power. Because remember, B to the A raised to this C power, let's say, is B to the AC power. So here, this will actually be B. The 20s cancel each other out. So whatever this number is, that's my B. All right, so let's plug this into our calculators. And it turns out to be 1.013, 9 equals B. Now the growth rate, though, is not that B. The growth rate is B minus 1, which means that we have 1.0139 minus 1, 0139, or approximately 1.39% per year. All right, and so what you can do now is actually rewrite this equation as N of T equals 110,000 times 1.0139 to the T power. So you can now figure out the value of the house at any point in the future, or any year for that matter, given that we started at 110,000 and therefore 1985 is year 0. We can theoretically now figure out the price of the house at any year based on this formula. And in fact, we're going to be doing exactly that, I see, because since T equals 0 is 1985, that implies that 2010 must be 25 years later. Therefore, look what we can do. Since we know that NT equals 1/10,000, 1.0139 to the T power, N of 25 now we just have to figure it out. So what you might want to do is multiply and figure out the value of 1.0139 to the 25th power. Now, it doesn't have to be perfect. You can do some rounding. So we have 1.4, 1, 2, let's say that's probably good enough. We multiply that by 110,000. And we get 155,335. And you don't necessarily need dollars and cents, but this is approximately equal to 40 cents, let's say. So give or take, now if you rounded it differently, you might have gotten a slightly different number of cents, but the price should be 155,335. All right. So that takes care of that one. All right, now what else do we have on this document? Oh, now this is a slightly different case. This is a car. Now, once again, this is our NT formula. So 2007 represents time 0. 2013 therefore represents time 6. The initial value is $38,000. Now, it's telling us that the value in 2013 is $11,000. So just like the previous question, we're not solving for the future value, we're solving for B. All right. Oh, sorry. Did somebody put in a chat and I didn't even notice it? Sorry about that. Hold on. Monthly is 12. That's right. Yes, exactly. When you have compound, I missed this before. Sorry about that. Yes, when you have compounding frequencies, 12 is monthly. That's exactly right. All right. Well, anyway, so yes, we're solving for B like we did before. And so what we actually have here is that N of 6 equals AB to the 6th power. So we have 11,000 equals 38,000 B to the 6th. So we'll divide out both sides by 38,000. All right, so let's figure out what this is. 11,000 divided by 38,000 is approximately 0.28947, let's say. And so now to solve for this, all right, so we choose the exponent 1/6 because that means that on the right-hand side we'll have B. Okay, so let's raise that to the 1/6 power. 0.289 8133, 3 threes, 26 equals B. Now remember the growth rate though, I just want to mention this, is B minus 1. And so you'll see that in this unusual case, B will actually be negative. Eight triple six. Now, of course, it makes sense here because we're looking at the depreciation of a car. Cars depreciate over time, as you know. So according to this, the value is dropping by roughly 18.7% every year for as long as you own it. So now, with all that being said, the actual question here is, what will the car be worth in 2017? So that means that 2017 would therefore be year 10. No, that's always the way it works. In other words, B is 1 plus. Let me add this to the bottom here. No, that's not the reason. B is defined as the growth rate plus 1. So therefore, the growth rate would be B minus 1. So whatever you got for B, you just subtract 1 to get the growth rate. Okay, so in other words, the formula itself is written in such a way that they want you to understand that B is to be interpreted as the growth rate plus 1. So therefore, if you have B, you know the growth rate by subtracting 1 from it. Now, the other 2 times we did this, or the other few times, we ended up with a positive growth rate. But you can have negative growth rates like the value of a car because of depreciation. So this is always true. That's right. Yes. So that's always the case. Anyway, so what we've just done here, we derived this equation. Now we have everything we need. N of t, A, we originally saw was $38,000. And B is 0.8133326. What was that? 3 threes. Now I lost it. There it is, 33326. That's it. I'm sorry, to the T. This is the general formula that we discovered. And now we can use it to forecast any year that we choose, including 2017, which based on what we the setup of the problem started in 2007. So therefore, 2017 is considered to be year 10. So the forecast will tell us that in 2017 or year 10, the value of the car will be and of course, we know that the value is going down over time. So it'll be worth less than it was in the previous example because we've had more time for the value to depreciate. So that works out to about 4,813.55, let's say. Okay, so And just as a reminder, n of 0 was 38,000. N of 6 was 11,000. N of 10, so you can see what's happening here. So if you were to plot this thing out on a graph, it would look something like this. At first, it falls off very rapidly, and then the rate of decay slows down so that 11, 12, 13, in those following years, the rate of decay would be much smaller. It would lose less and less money, and it can never become negative either. Okay, the car can't be negative, have a negative value. That would mean you'd have to pay somebody to take it off your hands. I don't know if that's really going to happen, but all right, anyway, so that one's done. And I believe that was the last question in this section, or this part of the problem set. Yeah, that was it. All right, now there's a second half to this, which involves algebraic operations on logs and exponentials. All right, so I mean, as usual, I'll post these solutions on Moodle so you can double check them later on, because obviously that's a lot of information to take in a short time. But I'm hoping that it's clear what we've done. And of course, you know, if it's not, you can always send me emails, or we can ask questions next week. Yeah, I think pretty much it's all here. The only ones that are really a mess are these first ones where we had to figure out the equation of the exponential function. And that's just because they're very complex functions. With straight lines, you don't run into these complications. You don't get b to the 6th power or something like that. But as long as you're careful, you shouldn't have any issues. And of course, you can always feel free to double check your results. I know it's a nuisance, but it sometimes is a very good idea. All right, so in other words, it just involves plugging the points into the function you discovered and making sure that it works. All right, so I think we're good here. Let's go get the other one. Number 2. Now these, once you've learned them, I mean, logs and exponentials, it's one of those things where after you practice enough times, suddenly it starts to make sense. It's like, it's one of those areas where you just have to get the hang of it. It's like, it's hard to memorize something like this. You just have to get to the point where you really understand what's happening, and that's only going to come from practice. Like here, for example, we're supposed to write these in exponential form. What does that even mean? Well, this first one, A, implies that 4 to the m power equals q. So what are you doing when you rewrite it in exponential form? This is now your base. This is now your exponent. And this is now the result. Now, just to make sure we really get this, what I'm going to do is throw in here a quick example with real numbers, which I think is the best and easiest way to do this. If I said log 10 of 1,000 equals 3, this is the same thing as saying 10 to the 3rd power is 1,000. So again, it's the same pattern. Here's the new base. Here's the new exponent. And this is your result on the right-hand side. So if you're not sure with these, you can try to make up your own numerical example and see if it works. So all four of these are exactly the same. You're doing exactly the same thing. Now the letters make it seem more abstract than it needs to be, but it's the same exact idea. In other words, here, for example, this statement is equivalent to saying that A to the C power equals B. All right, there's your base, there's your exponent, and there's your solution. Now, how about this one? This is telling me that 16 to the x power equals y. I don't know if these lines are helping or not, but you can see where the pieces are coming from. So these are basically, it's kind of like in the same way that 3x squared equals 4 is the same thing as x equals the square root of 4/3. I mean, it's really, it's just rearranging it. It means the same thing. Okay, so I don't know if that was a good analogy or not, but that's what I'm hoping will work for you. And then finally, this last one. This is the same thing as saying that x to the y power equals 64. Why? Because here's your base, here's your exponent, and here's your solution. All right. So you can see them all together one more time. Yes. Now here, they're going to ask you to do this backwards. You'll start with an exponential equation and work it back into a logarithmic equation. And so it's really just the reverse of what we just did. All right, so like, for example, here. So this implies that log 4 base 4 of y equals x. And so you see, it's the same setup. In other words, this is your base. This is your exponent. And that's your solution. And again, if it gets confusing, just remember an example that you know very well. Like this is one of my, I think this helps a lot because it's pretty obvious. The log base 10 of 1,000 equals 3 is equivalent to saying 10 to the third equals 1,000. So if you have an example in your mind, you can see that you can easily go back and forth between these two forms because you know perfectly well that 10 cubed is 1,000. They both represent the same information. All right, now, how about B? Well, based on what we saw here, you're going to have the log of this number applied to B equals A. So these are the same. These are the same. And the solution is this exponent. Okay, now C is different because we have e to the k. So don't forget, the log to base e is the same as ln, or natural log. So what that means here is that this is equivalent to saying, or first let me write it out like this: log base e of h equals k, based on the same rules that we've been using. But then what you would normally do is rewrite this as log h equals k. So I mean, you usually in most math books, log base e is written as natural log. You don't normally see it written as log e, but I wanted you to see that this follows the same rules as all the other ones. It just so happens to have its own special symbol, ln, or same notation. ln is natural log. Now, by the way, the reason why this is so important is because often you can more easily solve an equation by applying either logarithms to both sides or raising them, taking the exponential of both sides. So it's important to understand how these work. All right, and one more. And based on what we've been doing, we have log 19 of y equals x. And in fact, we're now about to get an opportunity to do exactly what I said. We're going to solve for x in each case by applying these rules. So if you look at the first one, for example, we know that the log to base 3 of x is 2. Therefore, what is the value of x? Well, we know that this can be rewritten as 3 squared equals x. Base, exponent, solution. And now, of course, this tells me that 9 equals x. Now, I don't think, it depends on the calculator you have. Some of them have a log button, some don't. They all have a natural log. So you can double check, I mean. Let's see. Yeah, even this Texas Instruments, I think it only has log 10 and natural log. That's kind of disappointing. I don't know how much more work it would have taken, you know. Yeah. All right. But anyway, that is the correct number. How about the next one? This implies that 2 to the minus third power equals x, because this is our base, this is our exponent, and this is our solution. And so 2 to the minus a third is equal to 1 over 2 cubed, which is 1 over 8. Okay. This one is equivalent to 5 squared equals x. And therefore 25 equals x. All right, and then let's see, there's one more here. And here, this means that 3 cubed is x, and that means that 27 is x. And that's it. All right, so I'll tell you what, it's 9:30. We may as well have our break right here. We're not done with this problem set, but we want to finish it up when we get back. There's still a ways to go here. All right, so okay, let's stop right here, and then when we get back, we'll start with section or problem 4. All right, so yeah, you can only do so much on an empty stomach, right? So, all right, we'll be back in a bit. Okay, I guess we can carry on now. So we're now going to simplify. Now these are based on the properties of logarithms that, let me just quickly review these real fast. So first of all, the log, and it doesn't matter what the base is, this is always true, of xy is the log of x time, plus the log of y. The log of x over y is the log of x minus, oh, hold on. I will, all right, well, all right, when we're done, I'll go double check. Before we log off, just remind me to double check. Yeah, I'll see if I can find them. Oh, as far as why are we doing it this way, I don't think there's any other way of doing these. They, well, the reason for doing these is usually what you're trying to do is essentially change this into something more convenient. So like, for example, let's say that, well, of course, these aren't numbers. It makes it a little bit awkward, but usually the motivation for switching back and forth is to make it easier to solve an equation. That's really the only reason you might ever do this. It's kind of like, you can think of it as going back and forth between dollars and pounds or something like that. You know, for certain applications, you need dollars, for certain ones, you need pounds. So here, sometimes it's more convenient to write this as a logarithm, and sometimes it's more convenient to write it as an exponential function. So there, usually the reasoning for doing this is just to keep things simpler or more straightforward. That's the only reason you do these. But it is important to understand how these are connected to each other. So not that you'll be doing a ton of this, but it is very important to understand how these are actually the same information. Oh, is there anything else? Oh, I think that was everyone. Okay, let's carry on. Oh, yes, so the last property that was the one where the log of x to the a power, where a is a constant, not to a, can be rewritten as a log x. Okay, so those are really three of the key properties that we'll be using with these expressions. And of course, remember, the purpose of this is to make things a little bit simpler. All right, so, and it's not always really possible to do that, but let's start with this first one. So what we can do here is recognize that since this is a sum, and now, by the way, we're assuming that they both have the same base. Okay, you notice how it's not written. Often in many textbooks, when there's no base written there, we're assuming that it's 10. But whatever the base is, as long as it's the same for both terms, we can apply all of these operations or simplifications. So let's just assume that these are all meant to be base 10, if they don't say otherwise. So what we're going to do here is essentially reverse this process. In other words, here, this implies that the log of x plus the log of y equals log xy. So if I multiply these together, I've got log 2x to the fourth times 3x. I guess I could write it like this. X to the fifth. And then you can just multiply them together the way you normally would. And so you would have here 6x, and the exponent will be 9. So you have to be careful with that. Whenever you have something like this, just a little side note here, when you multiply x to the a power, times x to the b power okay, so that's going to give you x equals x to the a plus b power. So algebraically, when you multiply two terms together that have the same base, you can just add up their exponents. So I just want to remind you of that very important property. And so that's why here, for example, I'm multiplying the 2 and the 3 to get the 6. The exponent is x to the 4 plus 5 power, which is just 9. So this is fine. I mean, this is, in this case, this is as simple as we can make this thing. So we may as well just leave it like this. And you can see sometimes the simplification means that it's only a little simpler. Sometimes it can make a significant difference. All right, but again, always remember this only works if the logs have the same base. All right, if they don't, then you have to do something different. Now here, we're going to reverse this property. This implies that, all right, let's do it this way. Log x minus log y equals log x over y. So that's what I want to do here. I want to rewrite this. And let me use my equation editor because it's easier to see it this way. Once it wakes up. So the log, the natural log, let's just write it again. Log 6x to the 9th minus log, and they're both natural logs, of course, which means they have the same base, which means we can apply these techniques. So now I'm going to have the natural log of the ratio of these two. In other words, 6x to the 9th over 3x squared and now we can simplify within this expression for the parentheses. And so what we'll end up with is 6 divided by 3 is 2. And now x to the 9th over x squared is x to the 7th. And so we'll review that in a second. First, let me save this. And that's because of this property. X, when you have a ratio like this, x to the a divided by x to the b equals x to the a minus b power. All right, so up here we had a product where we can add the exponents. Down here we have a ratio where we subtract the exponents. So that's why here, this x is actually equal to x to the 9 minus 2 power. So we have 2x to the 7th power. And I think you'll agree, this is slightly simpler than what we started out with. Again, it's not a huge difference, but it is different enough to make it worth our while to simplify. All right, now what about these two? What's going on with these? Well, we've got a sum. And so what we might want to think about doing here is this. We're going to take this formula or this rule, and by doing so, we're going to rewrite the first one as log x squared. Now, by the way, there's usually multiple ways of going about these. You don't have to follow this approach if you don't want to. So this would be log x plus 1 cubed and since it's a sum, we can rewrite this as log x squared times x plus 1 cubed And we could then, I think we should just leave it like this. I mean, this is, it's all one big expression. So, I mean, you could multiply everything out, but unless there's a really good reason for it, we may as well just leave it like this. I think most people, yeah. I mean, again, like I said, unless there's a really good reason for it, we may as well just leave it in this form. All right, now there's one more, yes. Now this one is interesting because it combines several of the properties we've been considering here. We've got a multiplication and a division. So basically, let's see, what can we do here? Well, first let's start out by rewriting this as log of x. And then we could write this one as minus log to the y to the 0.5 power. And then we'll write this one as log z cubed. Okay, so we've got both a multiplication and a division going on here because there's a sum and there's a difference. So what you end up with is something like this. Log. Now, what we're going to do is in the numerator, we'll multiply together log x and log z cubed because they are added together. So in the numerator, we have x z cubed. In the denominator, we'll have y to the 1/2 power because that is being subtracted. So we're basically doing two things at once. We're applying, we're doing a quotient, we're doing a product, and this is our final result. Oh, not what I wanted. There we go. All right, so again, I've got the x and the z cubed in the numerator, and I've got the y to the 1/2 power in the denominator because that one was subtracted. These were added, this one is subtracted, and so this is my final result. All right, now, these are going to be a little challenging. And these also are going to depend on knowing the properties of logarithms. All right, so what do I mean by that? Now, you notice for the first time, look what we've got here. X is in the exponent. How are we supposed to solve for this? Well, what we can do is take log to base 9 of both sides of this equation. I'm choosing 9 because this is a 9 right here. So if I do that, and I'm certainly allowed to do that, I can always apply any algebraic operations to both sides of an equation as long as I do it to both sides without changing my results. Okay, now what good does that do us? Well, let me show you one of the key properties of logarithms that this is based on. Actually, there's two. The log to any base of 1 is 0. So you can see where this is going. In fact, what I'll do is I'll put in a b there to indicate b is any base. Fine. The other one that we need to remember is this one, the log to some base a of a to the x power is equal to x. So it's almost like the log and the exponent cancel each other out. Now, that's what I'm hoping to take advantage of here. So in other words, why does this matter? Because the log to base 9, then of 9 to the x minus 10, is equal to x minus 10, and the right-hand side equals 0. So therefore, x equals 10. Now, in a case like this, you're probably going to want to do some double checking because this is a very complicated situation. So let's do that. Let's make sure that we're not imagining things and that this works. So let's plug in 10 for x and let's see if this works. So the x is replaced with a 10. And so you can see what I've got in my exponent is 9 to the 0 power equals 1. And of course, anything raised to the 0 power is just 1. 1 equals 1. And so it works. Now, this is a huge deal because all of a sudden we can solve for an equation that has x in the exponent or some function of x, whereas before maybe we couldn't do this. So, but it involves logarithms. And this is where logarithms suddenly start to appear to be very, very powerful, because what I was able to do is transform this disaster into this nice equation, x minus 10 equals 1. So the power of these logarithmic transformations is suddenly becoming very apparent, isn't it? Look how much grief you saved yourself. Now, there are other things you could have done too, but they would have been a lot more complicated. And let's say they would have introduced quite a mess. But I like the idea of using the logarithms because it just makes things so much simpler. All right, well, with that one being done, the others should fall right into place. Now that you know the secret. So for example, I've got 2e to the 6 x power equals 13. So what I would like to do is divide out that 2 and make things as simple as possible before I apply my rules. Oops. E raised to the 6x power equals 13 over 2, or 6.5. Well, we can leave it like this. All right, so now what do we do? All right, so based on the same reasoning we had up here, remember we had 9 raised to some power, and we took log base 9 to both sides. Here, I want to do the same thing, except I'm going to take log base e, which of course is the same thing as natural log. All right, so I'm going to do that to both sides of this equation. And I've chosen natural log because that is base e. Now, this reduces very nicely then. And it's almost as if, like, remember the log or the basic log and the exponent cancel each other out. We're left with 6x equals log 13 over 2. Actually, I'll use the equation editor for this. So that means that 6x equals the natural log of 13 over 2. And now, of course, it's pretty clear what we're going to do next. We'll just simply divide out both sides by 6. And we'll end up with x equals 1/6 of the log of 13.5. All right. Now, if you want to, you can convert this into a constant. Just go to your calculator. You don't have to, of course, but you can certainly take this log of 13.5 and divide by 6, and you'll get approximately 0.31197, let's say. So now, maybe we should do a quick double check. All right, so the original equation was this one. So I'll tell you what we'll do. Let's just put in there the that approximation and just see how close we get. So 6 times this number, 0.31197, means you've got 2e, and the exponent is 6 times that, which is approximately 1.871802, let's say. 13. Now, of course, I'll divide both sides by 2, and I'll end up with divided by 2 is 6.5. And now, how do I solve for this to confirm? Well, I'm not solving it. I'm just taking and going to my calculator and taking e and raising it to that power, 1.871802. And I'm hoping it'll be very close to 6.5. And it is. It's like 6.499999. And that's, of course, due to rounding. Close enough. That means we did our job. All right. So our final answer was this, which is approximately equal to this. And we can see from our double check that that's fine. Except this is only approximate. There's actually symbols. I don't know if there we go. Oh, okay, good. Remember those squiggly E's, that's squiggly E's, squiggly equals represent approximately equal to, if you've forgotten. All right, let me just put that in there as a reminder. All right, so we're going to do the same thing with all these other ones. But in each case, our best bet is always to clean it up as much as possible. In other words, we want to simplify it before we apply our logarithmic rule. Otherwise, we're just asking for trouble. So here, if I add 8 to both sides, I'll end up with minus 54. And of course, now I want to divide both sides by 5, negative 5. So I've got e. If I divide by negative 5, I'll have e raised to the 9x minus 8 power. And the ratio of those two is, well, we'll just leave it. The negatives cancel out, and we're left with 54/5. Now I'm going to follow the same procedure that I had before. I'm going to take the natural log of both sides of this equation. Because this is base e. Okay, that's why I'm choosing natural log. It's always going to have the same base as this number that I'm trying to solve for. All right, and that means that we have an interesting result here. The exponent 9x minus 8 equals this expression. And now just add 8 to both sides. All right, here we go. So 9x equals this log plus 8. And now I'm just going to divide by 9. Okay, so whatever that number is, I'll get out my calculator and approximate it. We can then double check like we did before. It's approximately 1.1532829, let's say. So in order to double check this one, I'll go back here and make sure that this is working out correctly. Oh, okay, now I guess what I should do here is use the approximation sign. All right, so I'll replace the x with that number. $1.153289829. 1.1532829. All right. Okay. So that exponent is approximately 2.379546. Man, this one is a nuisance to double check. All right, so e raised to that power times -5 is, -54. Oh, this one worked out really nicely. So therefore, -62 equals -62. Beautiful. So we did it. All right. So either one of these could be your final answer. They both mean obviously the same thing. All right, 2 more. Now, if you notice, most of these are natural logarithms. In practice, most of the time, you'll end up using natural logs rather than the other ones. You might see base 10 logs, but the others are fairly unusual. They're meant for more specialized applications. Like in computer science, for example, they use log 2 a lot, log 2 and log 16. All right, so here we'll subtract 2 from both sides. Divide out to 10. Equals 0.6. That's 6 over 10. And now I'll take the log of both sides. Okay. Let me just double check one thing. Yep. All right. Now, I want to take the natural log of both sides. So that means this just reduces very simply to the exponent, which is 8x plus 3. Now, the rest is pretty straightforward. I'll subtract 3 from both sides. And so the final result will be x equals, actually, I'll do my equation editor here. X therefore must equal the ratio of this whole expression, log 0.6 minus 3 all over 8. So whatever number that is, that's our final answer. And so based on the calculator, let's see what that's equal to. That's worth equal to approximately negative 0.4388532. Although if you want to be technical, I should be using these approximately equal to symbols. And now when we go back to the original equation to double check it, actually, let's just start from here. We'll plug in that number. The x becomes negative 0.4388532, and that exponent now becomes, let's see, e to the minus 0.5108. That should roughly equal 0.6. So I'm going to double check that right now. So that value is exact. Wow, this is amazing. It turned out exactly right twice in a row. How do you like that? All right. So it's 0.6. So that one's fine. And now we've got one more. Okay. So what's going on here? We'll add the 7 to both sides. We'll divide it to 4. And then we'll take the natural log of both sides. And then that leaves us with 3x plus 3 equals the log of 15. So we'll subtract the 3. And of course, at the end, we'll simply divide by 3. And that's approximately equal to let's find out. Log 15 minus 3 divided by 3 is negative 0.0973, let's say. So when we go back, let's put it in this equation. And we'll have e raised to the 3 times that value. And that exponent is now 2.97081. And let's see how close we got to 15 here. It's, oh, wait a minute. No, something's not right. Let's see. Oh, well, that would help. This is not correct. That's why, because this is actually 2.7081. That explains that. Okay, so when we raise the e to that power, it's 15, like almost exactly 15. So that one's done. All right, so this is your final answer right here. Now, in these cases, we're solving for x. Now, of course, In these cases, we're going to use the properties of logarithms. This is excellent practice. So in this case, for example, what we want to do is divide, of course, by 2. So log 7, x equals 2. Now, this is where those transformations suddenly prove to be really, really helpful, because this is equivalent to saying that 7 raised to the second power equals x. All right, so this is how we transform. In other words, these two expressions mean the same thing. And therefore, this is simple to solve for because 49 equals x. Well, it couldn't get any easier than that. But you can see we would have gotten nowhere without those properties of logarithms that we need. Now here, for example, I'm going to divide both sides by -8. So log 9x equals -2, which implies that 9 to the -2 power equals x. And of course, so 9 to the -2 is the equivalent of 1/81, or oh no, I divided both sides by 5. Yeah, all right, let me sneak that in here. Yeah, that's what I did. All right, now here, that's 1/81. You can turn that into a decimal if you want to, but that's the actual final answer. Now let's try this one. In this case, I'd like to subtract the 4 from both sides. And that's going to give me -2. So now this is telling me that 2 to the -2 power equals 9x. So this is the same thing as 1/2 squared. So I guess these are going to be messy. I'll use the equation editor. 2 to the -2 is the same as 1/2 squared. Or 1/2 squared equals 9x, which is the same thing as saying that 1/4 is equal to 9x. Now I can cross multiply, and I have 1 equals 36x, which means that 1/36 equals x. Whatever that number is, that's our final answer. All right, one more of these. Now, first, of course, I'll subtract the 6 from both sides. Then I'll divide out the 2. And now, of course, based on the laws of logarithms, this means that 2 squared equals 8x plus 4. or 4 equals 8x plus 4, subtract the 4 from both sides, 0 equals 8x, and therefore 0 equals x. All right. Nice. All right. Now for these, it's a similar idea. Except here, now what's interesting about these, you might recall, we had a series of these in the beginning. I forgot what chapter it was. And we can save some time here by noting that both sides have the same, in both sides, the log has the same base. So that implies that 10 minus 3x equals negative 4x. Okay, so if you have something like this, log base b, let's say, x equals log base b of y, implies that x equals y. Okay, so then it makes it so much simpler, because now all I have to do is add negative 3x to both sides, which means that negative 10 equals x. Now, certainly you can feel free to double check it. In case you're wondering, well, did this really work or not? Let's find out. Okay, so we'll replace that x rather, with negative 10. And that means the log of 10 plus 30 equals the log of 40. And the log of 40 does indeed equal the log of 40. So this must have worked correctly. But this is what we're doing up here. We're saying that since both sides have a log with the same base, that implies that these terms must equal each other. And that, you can see, that saved us a lot of grief. It's always nice when it works out that way. Nice. All right. So now, what about this one? So again, both sides are natural logs. So this implies that negative 3x equals x squared minus 6x So now I just have to do a little algebra. 0, I'll add that to both sides. So by adding 3x to both sides, this becomes negative 3x. Okay, so I can factor, well, this one actually has two solutions then, doesn't it? So that means that x equals 0 and x equals 3. And you can double check them both. I mean, you can see that in the first case, it's pretty obvious. If you replace the x's with zeros, you'll just get logs of zeros. Okay. So this becomes 0. And this becomes 0. And that reduces very nicely to log 0 equals log 0. And of course, you recall one of the key properties. Well, anyway, so this works fine. What about 3? So we'll have this. Replace that x with a 3. And when you simplify this, you can see that this is log -9 equals log of 9 minus 18, or log -9 equals log -9. So the double check works. Okay. Now, what about this one? Again, all the logs are the same. So therefore, all we have to do is rewrite this as x plus 3 minus x equals 74. Oh, now something, oh, you see now, I did not plan this one very well. Oh no, yes, that's right. I planned it very, did I do this right? Wait a minute, what happened here? Yeah, see this, no, there's a problem with this one. You can see it's not going to work out because this implies that 3 equals 74. So this problem is not set up correctly. So we'll have to get rid of it. It could have worked if I'd set it up correctly. This would have needed to be a constant though. Wow, that's pretty disappointing. So, all right, so C is an invalid question. We'll obviously not see that on any tests. Okay, but what if it had been set up correctly? Suppose instead it had looked like this. Log 10 of x plus 3, it would have been a nice problem. Suppose the second term had been log 10 of 3. Aha, now that's a different story altogether. Log 10 of 74. Because now you can see what we would have had. X plus 3 minus 3 equals 74. X equals 74. So this one is not correct. But after I fixed it, this is what it would have looked like. That's pretty annoying when that happens. Now here, another one, they've both got the same log. So therefore, all we do is write this as 6 minus x equals 3x, 6 equals 4x, and therefore 6 fourths equals x, or it can rewrite that as 3 halves, and you're good. So some of these are surprisingly simple. Now, part A, it looks like they're all essentially the same type of problem, so that's good. We're now getting pretty good at this kind of thing. So again, all these logs have the same base. X plus 12 equals x. Oh, well, this, of course, means that x equals 0. Yes, because if you double check it, so if you get rid of these x's and replace them with zeros, you'll see that these are, in fact, well, actually, now that I'm looking at it, no, this one didn't work out correctly either. I think this one was supposed to be, no, it's not right. Let's get rid of this one too. No, so never mind that one. All right, forget that one even exists. All right, let's instead go on to the next one. This one looks pretty valid. B. Now this one's different. We have to use the formal properties of logarithms. We can't get away with setting the two sides. In other words, like up here, it was easy. We just got rid of the logs in effect. But here we have to go back and remind ourselves how this works. So this implies that 2 to the third power, because of the definition of logarithms, equals 7x plus 6. 8 equals 7x plus 6. We subtract 6 from both sides, 2 equals 7x. And so therefore, 2 over 7 is x. All right, and there one more, and then we're finally done with this. Here, once again, we have all 8, log 8, so we can just write this as x plus 6. See, it happened again. All right, well, this one is wrong too, so let's forget it. This one should have been, we can fix this one though. If this had been, yeah, that was bad planning on my part. Sorry about that. All right, if this had been log 8 x plus 6 minus log 8 of, let's say, any number, how about 2? If it had been set up correctly, oh, thank you. So you would have ended up with x plus 6 minus 2 equals 58. X plus 4 equals 58. And then I subtract x from both sides. Yeah, so that's what would have happened had it been set up correctly. So, of course, I'll try my best to make sure none of these sneaks into the test. If they do, I just won't take any points off. That's all. Okay, so all right, so finally, we're done with this topic. Although I must say, this section, exponential and logarithmic functions, is really one of the truly most important topics that we've been going over, because in the real world, and especially if you get involved with business of any kind, these are critically important to financial applications and economic applications. If you end up in engineering, that's a different story altogether. Then the trig functions suddenly become critically important. And of course, you might end up in a field where there's no math at all. That's always a possibility too. Suppose you become a novelist and you are writing stories about, historical romances or something. Then it's not likely that any of this will show up in your work, but it's also good to have this knowledge, because when you're trying to analyze, for example, your investments in stocks and bonds, the more of this you understand, the better off you'll be. There's no getting around it. So one way or another, even though it might come to you in a very strange form, somehow this math knowledge can only help you, especially as the society becomes more technologically advanced. You don't want to be one of those people who has no understanding of any of this stuff, because it'll just make everything more complicated for you. So, all right, anyway, so let's put this away and get back to trig. I did find a nice video that'll explain one of the key concepts, or actually I think I mentioned already, there's 2. One is about how to actually calculate the trig functions, and the other is a quick overview of what types of applications you might find in the real world, which I think you'll find very interesting, because there's a lot of things in there you might not have ever thought about. Now, I know we did start to go over this last time, but it was 2 weeks ago. So let's maybe take a quick stroll down memory lane here. And so you've got the basic trig functions. And we also remember that wonderful, of course, nobody ever forgot what a right triangle is, with the hypotenuse being C. And this, of course, leads us up to our old friend, the Pythagorean theorem, a squared plus b squared equals c squared. And so, but yes, here we go. This SOHCAHTOA, this is the ultimate memory aid. Once it sticks in your memory, you'll never forget any of this stuff again. Okay, so remember what this means. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. Okay. So get it? OH, opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. Yes. Now, the ones that you do have to basically memorize, though, are the inverse ones. So, for example, these first two are obvious. Cotangent, cotangent, they're inverses of each other. These are the two that you might not, they might not make sense. Secant is actually the inverse of cosine, and cosecant is the inverse of sine. Okay, so this is how they're all defined. Now, you might remember that, when you're doing trig, you spend a lot of time trying to figure out the actual values of these trig functions for different angles. This is all about angles. Everything in this chapter is about angles. And yes, this is important for engineering and for architecture and a lot of real world applications, but not so much in finance or economics. So we also introduced a few new terms that you might have forgotten about. For example, for a typical angle, we have a starting side, we have a terminal side, and we have a vertex which connects the two. And the angle represents how much rotation we needed to go through to get from the initial side to the terminal side. If you notice, we're always going counterclockwise. Okay, so every quadrant that we reach represents another 90 degrees. So, for example, if we go from the horizontal axis up to the vertical axis in the first quadrant, that means we've gone 90 degrees. And then another 90 degrees brings us back to the horizontal axis. Another 90 degrees brings us back to the vertical axis. And then finally, 90 degrees more brings us back to our starting point. And of course, in this process, we formed ourselves a gigantic circle. And why is it all done in 60s? Well, because the Babylonians had their number system based on 60. And so this sort of came to be the standard way of doing things in trigonometry. And so we're kind of stuck with it. But, we're all kind of used to it now. Everything's in 60s. But anyway. Yes, so a single degree would be 1/3, 3/60th of a circle. Oh, and we also had this fun discussion about the origin, the equator being 0 degrees latitude and the prime meridian being 0 degrees longitude. Interestingly enough, now you might find this interesting. I have to go look up the name of this. I forgot the exact title. I think it may have simply been longitude. There it is, longitude, the story of a lone genius who solved the greatest scientific problem of his time. This was made into a movie, by the way. And what this is all about is during the US colonial days, the late 1700s, all the world's major powers were, of course, searching the world for colonies, and they were searching for spices, and they were searching for everything you could imagine. And there was a lot of trade going on. But the challenge was this: they had no way of measuring how far east or west they were. They knew how far north and south they were because they can tell by the angle of the sun. And they knew how to measure latitude, but nobody could figure out how to measure longitude. And so the King of England started up a contest where whoever came up with a solution first was going to win an enormous prize. And so this would be King George III. So he offered an enormous prize to the first person who can come up with an approach to measuring longitude that actually worked. Now, the holdup to it was, though, that in order to measure longitude, you have to have an accurate clock. You have to know what time it is to measure longitude. So the holdup was not so much the longitude itself, but accurate clocks. So a gentleman named John Harrison eventually came up with a clock that was accurate enough that he won the prize from the King of England. And in fact, the models of the clocks that he built are actually right now being stored in the Royal Observatory in Greenwich, where you can actually go see them if you're visiting the observatory. It's part of their museum. And so it's an extremely interesting story. And so they made it into a movie. So if you're interested in the history of science, it's fun. It's not boring at all. It's not in the least bit boring. They don't spend all their time giving you tedious details. It's really more about the challenge of finding the solution to this problem that was so important to countries, because it really made it harder for countries to trade with each other, because they'd be out in the ocean and they would have no idea how far it would be before they got to their destination. So this proved to be one of the most important developments in human history. And, on a par with discovering electricity, I would say. And so that's why this is such an interesting story. And so if you got nothing better to do one night, go check out the movie, or maybe even read the book, and you'll find that it's extremely interesting. Anyway, so let's get back to this. Remember that the longitude, the story of a lone genius who solved the greatest scientific problem of his time. So anyway, let's get back. Yes, so here's how we define our angles. We're going in a counterclockwise direction, and every quadrant moves us 90 degrees forward. And each angle can be measured in two equivalent ways. Coming counterclockwise, we have what are called positive angles, and moving clockwise, we can define what are called negative angles. So here's the 90-degree angle. This is what 90 degrees means. And you notice it forms a right triangle. All right, and of course, also don't forget the way the quadrants are set up. This is the first quadrant. This is the second. This is the third. And this is the fourth. Now, it seems backwards because we're so used to clockwise directions. Here, they're going the other direction. I don't know how this came about, but this is what we've done for centuries, and so we're going to keep doing it this way, even though it might seem counterintuitive. So here we have an angle which is both 225 degrees and minus 135 degrees. So in other words, if we go in a counterclockwise direction, we go through two full quadrants and halfway into the third quadrant, which brings us a total of 225 degrees. Going the other way, we go through one full quadrant and half of another one. So that's actually 135 degrees, but because we're going in the opposite direction, we call that negative 135. And if you notice, without the sign, they would add up to 360 degrees. And they have to. That's how you can tell which angles belong together when we're thinking in terms of positive and negative angles. All right. Now, another thing that we went over was the idea that if you go around the quadrants more than once, you'll end up with angles that are larger than 360 degrees. Like, for example, here, if I went around the circle a full second time and came back to the same point, I could think of this angle as 180, but I could add 360 to it, and suddenly it also becomes a 540-degree angle. And then I could do the same thing over and over and over again. But they all mean the same thing. So here's an example that I did with 90 degrees in the slides. If you look at this chart, you've got 0 for 360 and 360 mean the same thing. Going around 90 degrees is the same thing as 450 degrees, because I can add 360 to that. 180 degrees is equivalent to 540. And finally, 270 is equivalent to 630. And so like here, for example, with 90s, if I can just keep adding all the 360s that I want, and they all mean the same thing. So realistically, we don't, when you have an angle like 810 degrees, we try to reduce it to the smallest angle we can find, which is under 360. So here, if I've had a result of 810 degrees, what I would do is immediately convert it into 90. Because otherwise, it can get very chaotic if we're using all these enormous angles, especially because they all mean the same thing. So our job is basically to keep the angles from getting so large, and we do that by subtracting multiples of 360 until we get to the smallest angle, which is under 360, and that's what really uniquely identifies it. So this is just a point of notation or terminology, I should say. Quadrantal angles, I don't know why we need to know that, but those are the even ones. In other words, 0, 90, 180, 270, 360. Now, this is the part that really throws everybody for a loop. Radians, okay? Radians are an equivalent measure of angles. Now, in principle, this should be no more difficult than converting from Celsius to Fahrenheit, but I think that most people find this to be very difficult to work with. Degrees make sense. We intuitively understand what degrees mean. Radians, not so much. Now, if it helps to think of it this way, 1 radian is equal to approximately 57.3 degrees. And 2 pi radians represents the entire circle, which means pi is a half circle or 180 degrees. For some applications, it's more convenient to deal directly with radians. For others, degrees are the way to go. But it's like kind of like, I guess, learning a foreign language. Imagine yourself having studied Spanish in high school, and you find yourself going on vacation in Madrid for 2 weeks. Anytime you're forced to speak Spanish to somebody, it's going to be a struggle until you get tons of practice. And so the same thing is going to be true here with radians and degrees. We just have to keep practicing so we understand eventually the connection between the two. It'll never be natural. It's like radians are like our second language. It'll never be completely comfortable to us, but we can at least make sure we memorize the most important ones. Okay, that would be very helpful. Just try to memorize at least a few of these, and then that way everything else should theoretically fall into place. All right, so if 2 pi radians is 360 degrees, you can see algebraically pi radians is 180, and equivalently pi over 2 radians is 90, pi over 4 is 45, and then finally pi over 6 is 30. Now, if you have a calculator that can calculate trigonometry functions, let's say like you have the Texas Instruments series, I think it does have these capabilities in it. I just don't know exactly how to do that. But if you do have a very high-end calculator, it might be worth your while to learn how to use the trig functions, because at the very least, they can help you double check your results. So I'm looking at mine right now, and I'm not seeing any buttons that obviously, I mean, I see sine, cosine, and tangent. I'm just trying a quick experiment here. Yeah. Oh, I see what I did. Okay. So it does seem to work. All right. If you don't have one of these, I mean, that's fine. I mean, you don't really need it, but it certainly helps. All right. Well, anyway, so let's carry on. So pi over 6 radians, if pi radians equals 180, pi over 6 must be 1/6 of that, which is 30. Okay, so you can see you can convert them very quickly and easily as long as you remember this basic relationship. If you have to remember one of them, I would stick with this one. Pi radians means 180 degrees. And again, to me, it's really kind of similar to going back and forth between Celsius and Fahrenheit. If you've ever visited a foreign country where they use Celsius, you'll find yourself automatically in your mind converting all the Celsius temperatures back into Fahrenheit so that you intuitively understand what it means. So here, if you don't like radians, you can always convert them back into degrees so you can intuitively understand what they tell you. And when I say foreign countries, I mean basically every country in the world except the United States. There's apparently one or two small islands that still use Fahrenheit, but there's very few. Almost everyone else is on Celsius. So now here's a tricky one. 3/4 pi radians. Well, you're just multiplying 180 degrees by 3/4 to come up with 135. All right, now angles. Remember we were talking before about positive and negative angles. In this case, we see that 140 degrees is equivalent to 220 degrees. Why? Because they both stop at the same point. They both have the same terminal side. And again, if you notice that the sum of these two without paying attention to the sign is 360, so we know they must mean the same thing. These are called coterminal angles because they share a common terminal side. And so it's the same idea. I mean, if you come up with a result of a negative angle, you can always convert it into the equivalent positive version by recognizing how this works. And again, in many cases, that's exactly what you want to do. I don't know if my calculator would even accept negative degrees. Let me try this. I bet it won't. Sine minus 220. Oh, no, it seems to be perfectly happy with it. All right, well, I guess I misjudged my calculator. But anyway, yes, I mean, obviously you try to avoid negative numbers whenever possible in the real world. Imagine somebody asking you, what angle are you building your bridge at? And you say, minus 220. Well, I don't think you'd get very far with that. Oh, and we looked these up. Remember, you don't have to memorize these, but you might remember from somewhere in your travels that an acute angle means it's less than 90 degrees. We know that a right angle is exactly 90. And we know that you have this special notation for it. We always have this little symbol here that means this is a right angle. And then obtuse just means more than 90. And then we also have these other ones. Complementary angles add up to 90. Supplementary angles add up to 180. And this one, which I'd never heard of before, explementary angles add up to 360. How do you like that? Oh, the thing about math is there's a word for everything. Even if you've never heard of it, it's out there. It exists. Somebody has somewhere along the way has come up with a name for this concept that you're studying. You're not the first person who wondered what the name should be for this thing. All right. Now reference angle is, this is what I was talking about before. Remember, the angle's 90 is the same as 540. No, sorry, 450. And then the next one would be 810. If I keep adding 360s, 1170. And all of these are simply additions of multiple 360s to 90. In that case, we say that 90 is the reference angle of these other angles of 450, 810, 1170. All of those have a common reference angle, which is 90. Okay, so that's what we're going to call them. And again, we'll always, whenever possible, reduce all angles to their reference angles to make sure it's clear that we know what we're doing. All right. Let's see. Yes, so here's some examples. 740 is coterminal with 380, which in turn is coterminal with 20. And so the reference angle is considered to be 20 because after subtracting 360 twice, we wind up with 20, and it means the same thing. Okay, very good. Now, so again, remember, coterminal angles have the same terminal side. Now, what about with radians? Well, now remember before I mentioned that if you have two coterminal angles, like 140 and negative 220, without the sign, they both add up to 360. In terms of radians, 360 is 2 pi radians. So if you're dealing with radians, coterminal angles have to add up to 2 pi. So for example, 135 and minus 225 are coterminal. If you notice though, 135 degrees is 3/4 of a pi radians. Negative 225 is negative 5/4 pi radians. So to go from here to here, all I have to do is subtract 2 pi, and that's what happened here. Okay, so in other words, 3/4 pi minus 2 pi gives me another coterminal angle, which is minus 5/4 pi. All right. Now, what next? We sort of drifted a little bit into geometry, but let's just quickly look at this for a second because this could be important later on. We're going to look at circles very briefly. And so a circle has a radius. Remember, the radius goes halfway through. The diameter goes all the way across. The radius is half of the diameter. And so we have a radius, we have an angle theta. This S is some arc. Now, if you notice that it's light blue between these 2 points, we'd like to be able to figure out the length of this arc based on the radius and this angle. So it's not that difficult. In fact, let's see, what are we doing here? For a circle with radius r, the length of the arc is s, which in turn is defined as r theta. Oh, that's interesting. So s equals r theta. The length of the radius times the angle gives us the length of the arc. Interesting. And then we can figure out the area inside this arc with a very simple formula. Okay, let's jump down here. And therefore, based on the next diagram, you can see the blue shaded region, which we'll see in a minute, is our area. Oh, it's a very nice diagram. Just remember 1/2 theta r squared. And voila, there it is. So the arc is along here. The arc equals r theta. But the area is 1/2 theta r squared. Now, we should be able to figure this out for ourselves. I'll tell you why. You might remember from high school and your travel somewhere, that the area of a triangle, rather, is 1/2 of the base times the height. So this could be thought of as the base. The height. That would be the height. I think that is coming up in another diagram coming up. The height. So the base is R. So I think what's missing here is the height. According to this formula, it must be R theta. Okay. So that would give us 1/2 R squared theta. So it looks like they're implying that the arc equals the height of this triangle, which is therefore R theta. Now, I don't know if they're planning on proving that, but here's what they want you to see, though. They're going to introduce something called the unit circle. Now, the word unit just means one. So a circle with a radius of 1, whose origin is the, 0, 0, looks like this. And this is what we mean by the unit circle. The radius is equal to 1. Now, you might not think so, but this will prove to be hugely important as we calculate our trig functions. So just remember, the radius is 1. And this is a right angle, by the way. No, I'm sorry. No, it's not. It's I don't know what this angle is, but it doesn't matter because no matter what angle we have, the radius is always just 1. But the key detail is that it starts at the origin. So now we're going to use this information. Let me jump ahead a little bit and show this to you. Here's our unit circle. The radius is 1. Let's say the angle is t instead of theta. S is the arc. Now, within this triangle, remember the sine is the opposite over the hypotenuse. So that means opposite is this. So from the perspective of angle t, the opposite is this blue piece, which is the sine of t, and the hypotenuse is 1. So therefore, this is O for opposite, I should say. This is hypotenuse. So by choosing a circle where the radius is 1, we know that no matter what angle we're looking at, the height of that rectangle that is being formed here is the sine of t. And similarly, this base right here, this blue piece, because the cosine is a over h, and because the radius, the hypotenuse is 1, that implies that this must be the cosine of t. And with that starting point, we can calculate pretty much any cosines and sines we need, as well as tangents. So let's see if we've got an example here. Oh, by the way, there's one more piece of information we're going to need as we go along. You might remember this from somewhere in your travels. The sine of any angle squared. You might have seen it in terms of theta. Theta is just any angle, adds up to 1. here I've got it as t, but it's the same thing. This is known as the Pythagorean identity. After you know who, the Pythagorean theorem guy. So it turns out, though, that there's more than one of these, but this is the one that we need right now in order to help us figure out the sine and the cosine of any angle based on this unit circle. All right. Anyway, so this is getting kind of complicated here. So I'm kind of reluctant to dive into this right now because it's so late. So you know what we're going to have to do? Maybe, oh, and by the way, here's the unit circle, the diagram. This is the whole thing. When we're done with it, you'll see that you can use this circle to find any one of these sines or cosines in both radians and in angles. And so it'll prove to be a very useful tool. But of course, you know, it was much more important in the days when we didn't have calculators, for God's sake. So, but if you don't have the calculator with trig functions, this is fine. And so we're going to use this. And we're not going to spend a whole lot of time with trigonometry, just the basics, because we have bigger fish to fry as we go along. I seem to remember chapter 9, which is next, is our discussion about linear equations and solving simultaneous equations. So we definitely want to get to that. We'll start for sure that next week. So what we'll do is we'll wrap up this discussion of trigonometry by going through this unit circle very quickly and very carefully. And then we should have plenty of time to dive into 9. And so, yeah, I mean, this will be our first and last look at trigonometry in this class. After that, we'll have other topics to look at. But so I think it might be a good idea to knock it off right about here, because what's coming up is fairly involved and it's, you know, pretty late, let's face it. So I'll post the solutions that we just put together on Moodle. And then next week, you know, what you should do is just go through the slides and make sure you understand what we're doing. All right. So how was that? After a week off, it seemed like a long time, didn't it? But we're back in the saddle now, aren't we? Yes, we are. Our math skills are sharp. So, all right. So I guess I'll just see you all next time. Oh, there's one person who had a question about their test, if I got it or not. So that person should stay behind so we can figure this out. Everybody else, if you don't have any more questions, I'll see you next week. Hello. See you later. Bye.
Thank you for your time, Professor.
Okay, you're welcome.
Hey, Professor Anderson, I was just wondering if you got my test as well.
I will double check that right now. I'm going to say probably, but I will confirm it. I thought I will, since there's so many of them and they're so long, I will almost not be able to do them until this weekend, but I can at least go back and make sure that it's in there. Did you send it to my purchase account?
Yeah.
Okay. Now, the thing that I'm concerned about here is that I'm always running out of space. My purchase account has so little room in it that I'm constantly running out of space. So let's see. There you go. It's there. You're good.
Okay, awesome. And yeah, I'll let the other person go first. Yeah. Cool.
All right.
Thanks.
Okay, bye. And there was
Can you
somebody.
double check for mine as well? I got a strange response when I tried to email.
Oh, all right.
the
I
first
can't
time.
see your name. Is it Theo?
Theodore. It'd be under Theodore. That's what my email address.
And what your last name is?
Hagel. H-A-E.
All right. Yeah, it's here. I can see them.
Okay, perfect. Thank you.
Okay. Anyone
Have
else?
a great day.
All right. Bye. Sydney Lawson. That's right. All right. Let's check yours. And by the way, if I don't have it, it's not your fault. I wouldn't mark you wrong or, you know, mark it late. Here it is. It's right here. You're good. Okay. Was there anyone else? All right. If not, then I'll see the rest of you next week.
Hey, Professor Anderson, I just have one more.
Yes. Yes, go
I was
ahead.
just wondering, do you teach calculus class as well?
Unfortunately, they don't normally let me. Yeah, I would love to do that, but no. You know why? Because my PhD is in economics, and so they try to only give me basic math classes. They usually try to
Okay.
reserve calculus for the full-time faculty members, because I'm actually being shared between the math and the economics departments. And
Okay. Okay. Cool. Because I was trying to take your calculus class.
I know I would love to teach it, but they're not likely to offer it to me, because I most of the time I do math for contemporary life, which is not meant for
Okay.
the majors. So
Yeah.
I love it, but unfortunately I don't think it's going to happen.
Okay. Okay.
All right.
Cool.
Okay.
Thanks.
I hope that
Saturn.
means that you're finding this to be very straightforward.
Yeah. Definitely. Definitely.
Nice. That's all I could ask for. Is it if it's straightforward, I don't care about anything else. That's what I want. Okay.
Yeah.
All right. So I'll see you later.
Thanks.
All right. Bye.
Hi,
Oh,
Professor.
hello. Yes.
Hello.
Is
My
this Emily?
internet. I'm Yuki.
Yuki. Okay. Okay. Let me find. You're looking for your test.
No, my internet connection is so bad, and I couldn't join the first one. I just want
Oh.
to say that. I'm so
Okay.
sorry.
Oh, it's all right. It happens all the time. Don't worry about
Yeah.
it.
And did you get my test?
Let's see. I'm not so sure. I'm not seeing. Did you send? Which email address did you send it to?
Yuki Ibata Yeah, I think I sent your Gmail address.
That's okay. I'll find it. There it is. I have it. I have it. You're good.
Okay.
Right.
It's good.
See you
Thank
next
you.
time. All right. Bye. Anyone else? Okay. See you all next time.